Good morning, everyone. So let's get started with our question for today. So this problem features two objects instead of just one object. So this system here is motionless. What is happening is that the 200 Newton block is on a ramp and is being it's attached to a cable hanging over a pulley that is also attached to object B. So B is attached to object A, to the two mass of 200 newtons, with a weight of 200 newtons. So we want to figure out what is the mass of block B. Now this system here is in equilibrium because it is motionless and the ramp and pulley are frictionless. So basically nothing is happening in this problem. So the question is essentially, what is the mass of B, and what is the mass of B that allows this system to be completely boring and have nothing happening? Then I want you to answer, how does this answer change if the angle is increased to 70 degrees? But that one should come pretty easily once you're able to do A. So I will give you a couple of hints for this problem because I realize that this problem may be a little bit more challenging. So this is a two object problem. So when there is a two object problem, you will want to draw a free body diagram for each object and then solve a set of equations for each object, right? So there's not going to be one magical solution that has all the forces together. You will need to solve a separate set of equations for each object. Additionally, right, a lot of the times you won't be able to solve for a force or something directly. It's sort of one of those things where you'll end up getting a system of equations that you then can use to solve for a force. So for example, you might want to be solving for, I don't know, like a normal force or a tension force or whatever, right? And then you realize that I don't have enough information to solve for this. It's easy to look at that and be like, I'm stuck. I don't know what to do. But make sure you get as far as you can in every single direction, and then eventually you'll probably end up with something like a system of equations, which you then can solve. So the idea is to try to get as many relationships as you can between the quantities and then solve for the forces. So that's something I would recommend, is don't try to solve for the forces. I mean, you can if sometimes it will work. What I would recommend though is to try to solve as far as you can in each direction, try to get as much information as you can. You're really looking for relationships between these different quantities, and then trying to solve for the forces. So that is the hint I will give you. I will show you what I mean when I do the problem on the board. But for now, try to solve as far as you can in each direction before you try to actually solve for the numerical values of each force. So that's something I would recommend. Yes. The reason why I say this is because, again, it's very easy to be, let's say there is an object C and you're trying to solve for its something in a diagonal direction, and it's easy to do it and then realize I can't go any further. I'm stuck, and then just be like, I don't know what to do. So you may be stuck in that direction, but that doesn't mean you are stuck in another direction. So get as far as you can in each direction before you give up. Yeah.
Sorry, I just want to make sure that I get it right. So the 200 newtons, is that pulling on the pulley at an angle? Is that what's currently going on?
That's the weight of the object. So like that's basically that's mg for that object.
Oh, so that's the force of gravity.
Yes, the force of gravity without any slopes. Yeah. Okay, so I am going to start slowly working through this. If you're still working on it, that's okay. I'm gonna do this pretty slowly so you can still continue working on it. So what I drew, oh, I should also change the view so you can actually see what's going on. I should turn on my camera so you can see what's going on. There, you can see everything. Okay, cool. So to get started, what I like to do is I like to always draw free body diagrams. So in this case, we have two objects. I affectionately call this one A. So let's call this A and B. So let's draw free body diagram for each one. I'm first going to start with B because B is easier. So with B, we always have the force of gravity, nothing special here. And in the case of B, there is a cable pulling it up, so we expect that there should be some sort of tension. And that's it for B. B has no other forces acting on it. What about A? So A is at an angle. So let's draw some forces acting on A. So I think it probably makes more sense to draw this A rotated slightly. So A has the force of gravity going. So A has the force of gravity going straight down, as always, nothing special. Additionally, A is on a ramp, right? And the A is not falling through the ramp, which means that the ramp needs to be pushing up on A in order to keep it above the ramp. So there's going to be a normal force perpendicular to the ramp. Additionally, A is being pulled up by a cable. And there's no friction in the problem, so we don't need to worry about friction. And then that is all the forces we need for A. So looking at B, I think B looks pretty simple. We don't really need to do anything to B. A looks okay, right? We have a ramp here. We have the tension, which is parallel to the direction of motion. We have the normal force, which is perpendicular. However, the force of gravity here is not perpendicular. It's at an angle. So that means we should do something to the gravity to make it more usable. So what we're going to do is we're going to use our little bit of our trig knowledge here, and then we are going to try to decompose gravity into a more usable manner. So basically what we want to do is we want to use a little bit of trig here. I want to draw a triangle here that allows us to decompose gravity into perpendicular and parallel components. So this is the ramp and this is the force of gravity here. What I can do is I can draw a right triangle with this side being perpendicular to the ramp, and then this side being parallel to the ramp. And then using my alternate interior angles thing, I don't know what the thing is called, but this angle is also 35 degrees. So if we call this side the perpendicular side and this side the parallel side, what I'm going to use is I'm going to use a little bit of trig to figure out how much the force of gravity is used to push the object into the ramp and how much of it is used to pull the object down the ramp. And so the cosine of this angle, so the cosine of this angle, which is the perpendicular side right here, the cosine of this angle is 35 is equal to the perpendicular force over the force of gravity, which is the hypotenuse. Rearrange this a little bit, so I know that the perpendicular force should equal my force of gravity times cosine 35. Something very similar for this side, for the parallel side. The sine of this angle should equal my parallel side. Parallel should be like this. Parallel side over my force of gravity. So my parallel side should equal my force of gravity times sine 35. So now what I've officially done is I've officially broken down this force of gravity now into a parallel component, a perpendicular component, and a parallel component. The perpendicular component, as we found earlier, was force of gravity times cosine 35. And the parallel side here is what we found is force of gravity times sine of 35. All right. Does anyone have any questions on the free body diagram so far? How I decomposed gravity, how I made it into usable forces? Is this part reasonable? I think this part is reasonable, I think. Okay, so let's go to the next part. So I think this part is doable, right? You just draw some free body diagrams, decompose gravity a little bit. The next part is going to be more mathy and it's harder to set up. Okay. So what I am going to do is I am going to start with B because B looks easier. There's only two forces here. B also has its forces only in one direction, the vertical direction. So that means when I'm setting up my equations for B, I can just ignore the horizontal direction altogether because B is not going horizontally at all. So I only have to work in the vertical direction, which makes my life a little bit easier. So what do we know about B? Well, the only thing we know about B is that the system is motionless, which means that the sum of all forces in the y direction, in the vertical direction, should equal 0. Net force acting on B should equal 0, which is just another way of saying that the force going up minus the force going down. So the tension force going up minus the force of gravity going down is going to equal 0, which is another way of saying that the force going up should equal the force going down. And we know that the force of gravity should be equal to m times g. Okay, and we want to solve for m. So so I'm looking at this, and in order to solve for m, I need to know what tension is. Okay, I'm stuck. I don't know what to do now. So I'm stuck. I don't know what to do. So it's easy to look at this and be like, I don't know what to do. I need tension, and I don't know how to find the tension. And it's easy to say, okay, I'm done. I don't know what to do here. So here's the thing, right? We may be stuck in this direction for this object, but notice here how we haven't done anything for the A object yet, right? We still have information we haven't used for A yet, right? So we may be stuck for B, and in this case, we're only stuck in the vertical direction, and we need to figure out this tension force, but there's no way of figuring it out from the B object. So we need to use our information from the A object. So if you're ever in a situation like this, where you're like, I need to know what this force is in order to figure out what this force is, you have to look at the other direction as well for the other objects and make sure that you are exhausting all of your information for these. So even though I can't figure out what tension is for B, I can still maybe figure it out from A. So I start with B, I ran into a dead end, I'm going to go to A now. So for A, let's go with let's first start with the perpendicular direction here. So in the perpendicular direction, the sum of all forces in the perpendicular direction is also going to equal 0. Why? Because the object is motionless and it's not going above the ramp or into the ramp. So that means the sum of all forces in the perpendicular direction should also equal 0, which just means that the force going above the ramp minus the force going into the ramp should equal 0. Which is another way of saying that the force going up above the ramp is going to equal the force going into the ramp. Okay, so now I have an expression for the normal force. We know the force of gravity here, this is just 200. So the normal force should equal 200 cosine 35. Okay, so now we have an expression for the normal force. But when we were trying to figure out our mass for block B, we needed the tension force. So what we did here was not super useful. I mean, we did figure out a normal force. Maybe we'll use this in a second, but as of right now, this is not very useful. So which means we still need to go and finish out the last direction before we can give up, right? So before we can give up, we still have to go to finish up the last direction here. So in the parallel direction, how do we set this up? Well, once again, the system is motionless. It's in equilibrium. So which means everything needs to cancel out, which means the sum of all forces in the parallel direction should equal 0. Right? So this whole system is in equilibrium, which means that every single time I'm setting an equation, I can already say the sum of all forces in that direction for that object is 0. Okay, so what do I do now? Well, that means since the sum of all forces is 0, this means that the force going up the ramp is going to minus the force going down the ramp is going to equal 0. So the tension force going up the ramp minus the force of gravity going down the ramp is going to equal 0. Notice here I decomposed this gravity so that it's the sine of 35 rather than the force of gravity. A common mistake is to just say that the force of gravity is going down the ramp. However, that's incorrect, right? We actually had to decompose it first, right? So we decompose it. So now that we have the force going up the ramp is going to equal the force going down the ramp. Okay. So now we actually have an expression for tension. So can we actually solve for tension here? Yes, we can, because we were indeed given the force of gravity for the A object. So our tension is indeed the 200 times sine of 35. Now we have an expression for tension which we can now use to solve for our force of gravity. Mass of block B. So I am no longer stuck here. I actually have something I found for tension. So you're no longer stuck. So our expression for the tension, as we found earlier, was 200 sine of 35. And this is going to equal my mass times gravity. So I'm going to divide both sides by g. And so I get a 200 sine 35 over g is going to equal my mass. And if I remember correctly, it should be something like 11.7, I think. So does anyone have any questions here?
Yeah, I have a question. How did he get the force of gravity to be 200? Is that just because that's the
That's
force
just
from
given.
outside? Oh, okay.
It's just given, yeah. So it says here on the big block, 200 newtons. So when it says 200 newtons, that just means that the weight of the object, the force of gravity on the object, is 200 newtons.
Okay, thank you.
Any other questions? One thing I want to point out is that we found the normal force here. We never actually used it. So it's okay, right? It doesn't mean that you did anything wrong. It just means that we found something that we didn't necessarily need to use. If this problem did have friction, we would probably have to use the normal force here. But in this case, we got lucky. There was no friction in this problem, so we were actually okay. So the last part B of the question is what happens if the angle is indeed changed to 70 degrees, I believe. So the only thing that would change is that instead of our answer being 200 sine of 35, it would just be 200 sine of 70, which means that our mass should be 200 over g times sine 70, which means that our answer should indeed be all right, give me a second, times sine 70. It should be 19.2. Which makes sense because if this angle was steeper, right, A is going to want to slide down more. So in order to balance out the sliding of A, you're going to need a bigger object in B. Okay. Okay, so that was a bit of a, how would I describe this? A bit of a doozy? No, I don't know if that's the right word for it. Bit of a challenge, yes, but I don't know if I have a more fun word for it. So, what are the pitfalls of this problem? I think one of the challenges you will run into is, when you get stuck on any particular direction and you don't know where to go from there. The way I can rectify that is make sure you exhaust all the information in all the different directions before you give up.
I have
So-
a quick question actually.
Go ahead.
So on your first diagram on the board and on the diagram on the slides, there is that little ball that takes a rope and makes it go around.
Yeah.
If the ball was bigger or smaller, would that affect the result?
Okay, so in reality, yes. In this problem, no.
Because there's no friction, right?
Because there's no friction on the
Okay.
rope on the pulley. Yeah.
Okay.
Yeah. Okay, so good question. What are some other pitfalls here? Another pitfall is trying to do everything in one go. I actually had to notice how here I actually had to set up 3 different sigma equations before I could actually solve the problem. So while the problem itself is not necessarily mathematically difficult, I think what's hard is knowing to work in all these different directions and then knowing to essentially combine information from different models. So here we essentially had a system of equations where we had one system being T is equal to N, tension is equal to mg, another system being tension is equal to 200 sine 35. So that's another thing that you might run into is you have a system of equations that you need to solve. But in general, the idea is the same for any sort of problem. For every object in the problem, you will need to draw a free body diagram to help you visualize the problem. And then you will also want to set up a system, essentially multiple equations for each problem, for each object in each direction. Once you do that, you should be able to combine a direction. One thing that is helpful for this problem is that the tension in the rope is always the same here. It's just one rope, it never changes. So the tension that was pulling A up is the same as the tension pulling B up. So the tension of the ropes are the same, which is if the tensions were not the same, this problem would not be solvable. Okay, so that is for this problem. If you don't have any other questions, what I am going to do is I am going to move on here to the next problem. This is the one that we started last week. This is the one where you have a block on a table essentially, and then you have a ball hanging from the table and like the ceiling or whatever. And we need to find the frictional force between the tabletop and the block and the tensions in the ropes. So we started this last week. What I'm going to do is I'm going to give you some more time to work on it while I clean the board and get ready to solve this. So the tips I have for you for this problem is now that you probably have a little bit more comfort with doing 2 object problems, I encourage you to do something similar to what we just did. Set up free body diagrams for each object, solve a systems of equations for each object, and then come up with your answer. So I will actually let you figure this one out before I do it on the board. So yeah, take a few minutes, see how far you can go here before yeah. Is the magnitude of the frictional force just frictional force? Yeah, that's what I mean. The magnitude of the frictional force is just the frictional force. If so, is it equal to this? Also, I got this and this. Yes, I will do it in a second. I think that's correct. I'll do it in a second to verify it. Okay, so let me erase the board and then I will do it. We can do it. We can do it. We can do it. Okay. I am running out of space here. This board is a little small for what I'm about to do. Okay, so actually in this case. Okay, so let me just quickly draw out the problem here. Block. Let's call this block A. Tension. Cable. I don't know, roof or something. Ball. Okay. So okay, so how do we start this problem? To start this problem, let's first draw free body diagrams because that's what we do in this class. We like to draw. So how do we start off? We have two objects. We have the block and the ball, A and B. So we should draw a free body diagram for each one. Why do we draw free body diagrams? To help us visualize the problem, to see which direction forces are going. So I'm first going to start off with drawing B because why don't we start with B? I don't know. Why don't? So B has a force of gravity going straight down as always. We have a tension pulling it to the left, T1. And then we also have a cable pulling it up and to the right at an angle, T2. So that is B. Let's draw A now, the block. So the block is on the table. We got a force of gravity going straight down as always. It's on a table. The table is preventing it from falling through the table. So there's a normal force going straight up. There's a tension force going to the right. And then and then there is also the frictional force on the table. So so the cable is pushing the block to the right. So in order to resist that, the frictional force needs to go to the left. Right? The cable wants to pull the block to the right. So in order to resist the change, we need to have a frictional force going to the left. Okay, so this looks doable. A looks doable. B does not look doable. The reason why B is not doable is because our tension to force is at an angle. So what do we need to do? What we need to do is we need to
Wait, Mr. Hu?
Oh, sorry.
Does tension 2 not pull up on A at all?
It does not. It does not pull on A at all.
Okay.
Yeah. Yeah. Okay. So to decompose B, what I'm going to do is I have an angle here, T2. And the T2 is the hypotenuse of a right triangle here. And what I want to do is I want to break down this diagonal force into a horizontal and vertical components. So in other words, I want to find what the Y forces and what the X forces. So using a little bit of trigonometry, the sine of 30 degrees is going to equal my Y over T2. So Y is going to equal T2 sine 30. Something similar for X, the cosine of 30 degrees is going to equal X over T2. So T2 cosine 30 is equal to X. So now what I've officially done is I have officially broken down T2 into T2 into cosine, hold on, T2 cosine 30, and then T2 sine. Okay, so now that we have two free body diagrams here, we can now solve for the problem. Do we want to start with A or do we want to start with B? I don't know. Let's do it well, we want to solve with a frictional force. So why don't we start with A? So, this vertical and horizontal. So let's first start with A. So we want to solve for the frictional force. So which means we're going to be looking in the horizontal direction here. So the whole system is at rest, which means everything is in equilibrium, which means the sum of all forces in the horizontal direction should also equal 0. So the force pulling to the right minus the force pulling to the left should equal 0. Force pulling to the right is the tension force from the cable, T1. And then the frictional force is resisting that. So this is the long-winded way of saying the tension should equal the force of friction. So as long as I can find the tension in the spring, I should be able to find the force of friction. Okay, so I am not done here because I need to figure out the tension force in order to figure out the frictional force. And I am sort of stuck. Okay, so what can I do from here? Well, I am done in the horizontal direction. There's nothing else I can do here. However, there are three other directions that I might want to look at. What I think the logical thing to do is let's look at where else can we find T1. Well, we can also find T1 in B, in the horizontal direction for B. So we're going to do is we're going to jump to the horizontal direction for B because that's where we can also find T1. We're using a little bit of detective work. So we know that we're looking at B now. So the sum of all forces in the B for B is also 0. So the sum of all forces in the B direction is also 0. You can just say the same thing for the vertical direction for B and for A because the system is in equilibrium. So the sum of all forces in the x direction for B is 0. That means the force pulling to the right, which is T2 cosine 30, minus T1 should equal 0, which is just saying that T1 is going to equal T2 cosine 30. So we now have an expression for T1. However, in order for to figure out T1, we need T2. So we are once again sort of at a dead end. Okay, so are we stuck? Are we still stuck? No, we still have two more directions to go. So what we're going to do is we're going to try to trace where T2 is. We know that T2 is down in the horizontal direction of B, which we just did. However, we did that and we didn't get anywhere. So we also want to figure out where else we can see T2. Oh, it's also in B, but in the vertical direction. So if we can work out what T2 is for B, we will be able to figure everything else out. So the sum of all forces in the vertical direction for B is 0, which means that the force going up, T2 sine 30, minus the force going down is going to equal 0. Well, it's just another way of saying the force going up should equal the force going down. So what is the force going down for B? Well, B weighs 8 newtons. So T2 sine 30 should equal 8. Sine 30 is 1/2, so T2 times 1/2 is going to equal 8. So T2 should equal 16 newtons. So now that we have the expression for T2, we can now figure out what T1 was. So T1 is just going to equal 16 cosine 30. 16 cosine 30 is 13.86. Okay. So now that we are done, now that we have the force of tension for both strings, we can now figure out what the frictional force was. Well, we found out the frictional force was just equal to T1. So that means our frictional force is also just going to equal 13.86 newtons. And is that all we were looking for? Yes, that is all we're looking for. So notice how we did not need to do anything for A in the vertical direction. We actually sort of skipped it. The problem was only asking for the magnitude of the frictional force. We weren't looking for the coefficient. If we wanted to find the coefficient, we would go to A in the vertical direction, and we would try to figure out the normal force. But in this case, we were just looking for the frictional force. So that is how you do this problem.
Wait, so Mr. Hu,
Yes, go ahead.
so just to clarify, we use the weight of the ball as like the force of gravity.
Yep.
Okay.
Yep. As far as why T2 is not pulling the block up, I know we had an earlier question about why T2 is not pulling the block up. It's like I don't know how to. I'm trying to figure out a way to describe it. Like imagine if the block was like, I guess it's just because the T2, it's like the cable is not attached to the block directly. Like the T2 is attached to the ball, but it's not attached to the block. So T2 technically doesn't have an effect. T2 has an effect on T1, as we found, right? T1 is dependent on T2, and then T1 affects the block, but the block itself is not attached to T2. It's like a causation correlation thing, maybe. So like T2 has an effect on T1, and T1 affects the block, but T2 doesn't directly affect the block. I think that's the best way to describe it. Yeah. Okay. So I think overall, I think we are in a decent place. Let us do one more problemo. I think. Oh, does anyone else have any questions for this one? Anything else I can answer? Yes. Also, usually I will give you the mass, but sometimes you might be given the weight of the object instead. And so it will be important for you to be able to make that distinction as well. In this case, so we are, in this problem, we are indeed given the masses of the next problem. Okay. So this is probably the, how do I describe this one? I would say this is of comparable difficulty to the ones we just did. So we have a two block pulley system thing. If you notice here, this is actually pretty similar to the last problem. And the problem before that. This is actually, a lot of these problems are actually fairly similar to each other. So we have a hanging 1 kilogram mass, which is M2. So M2 is 1 kilogram. This is a weight. This is a mass this time, not a weight. And M1 is 4 kilograms. So the M2 is attached to M1 via a cable. So if the coefficient of kinetic friction between M1 and the tabletop mu k is 0.2, what is the acceleration of the blocks? Then we will need to figure out what the tension in the cord is. Then you will need to figure out what the minimum value of the coefficient of static friction is in order for the block to remain motionless. And then what is the acceleration of M2 if the mass is doubled. Okay, so let's first start with A first. So let's first find the coefficient of kinetic friction between M1 and the tabletop. You may need to figure out the tension as well. Okay, so I'm going to start doing this problem. I'm just going to first work out the easy parts. Easy part is the free body diagrams. These will be the easiest free body diagrams we will be doing in a while. Why? Because there are no angles. M1 is pretty simple. We just have T1 pulling to the right, force of gravity pulling straight down, normal force pulling straight up, and then we have the force of friction resisting the motion. Right, there's no angles here, pretty simple. M2 is even easier. We just have force of gravity going straight down, and then we have the tension going straight up. Pretty straightforward. The next part is actually going to be quite a bit harder. Why is it going to be harder? Because the first thing we can no longer assume is we can no longer assume that the system is in equilibrium. Why? Because we are actually trying to find the acceleration of the blocks. If there is acceleration, it means that the system is no longer in equilibrium, which means that the sum of all forces is no longer going to be zero. So let's first start with M2 because M2 is easier. We only have two forces to work with. So the sum of all forces for M2 is going to equal its mass times acceleration. So normally this would be zero if it's in equilibrium, but it's in this case we can no longer assume that it's equal to zero. So the sum of all forces for M2 in the y direction is going to equal zero, which means that the force going down minus the force going up is going to equal my mass times acceleration. Means that M2g minus tension is going to equal M2 times A. Now, I set up this so that the force of gravity comes first, because I know that the system is going to start accelerating downwards. If you set tension first, you would get a negative acceleration, which is the same thing. So one of them, if you put gravity first, you'll get a positive acceleration, which means that the system is accelerating downwards. If you put tension first, you are getting a negative acceleration, which is also meaning that the system is going down. So it doesn't matter which one you put first because you'll end up getting the same answer. You just have to interpret the answer. Okay, so now we have an expression for the acceleration. However, we can't do anything here anymore. So we know what M2 is, I believe. We know what G is. We know what M2 is. We don't know what tension. So if I want to find the acceleration, I need to find the tension. So let's go to M1 here. Let's start with the vertical direction because the vertical direction is pretty easy. And so this case, the sum of all forces for M1 in the vertical direction. In this case, it is zero. Because while the system is not in equilibrium, and for M1, it's accelerating, but it's not accelerating up or down, right? It's being pulled to the right, it's not being pulled up. So the sum of all forces in the vertical direction for M1 is going to equal zero, which just means that the force going up, the normal force, is going to equal the force going down. So the normal force is just going to equal mg. So that is pretty simple. That's pretty much like a lot of times we can sort of already know this. Let's go to the horizontal direction next. So the horizontal direction, the sum of all forces in the horizontal direction is going to equal its m1's mass times acceleration. Once again, we can't assume that the system is in equilibrium, so we can't assume that that this side is going to equal zero. So what the sum of all forces in the horizontal direction is we have the tension force minus the force of friction should equal my m1. So my force of friction is just my mu k times mg is equal to m1 k. So now what we have is we have a system of equations. So the accelerate, one thing that you will need to realize is that the acceleration for both M1 and A are going to be the same. Acceleration for M1 and M2 are going to be the same. So the acceleration here and the acceleration here are going to be the same, right? Because as M2 is pulling down M1, right? So they're both going to sort of fall together at the same rate, right? It wouldn't make sense for M2 to be following. I guess if we were thinking about it as like, you know, like we're assuming that the M2 is just pulling down M1 like perfectly. Yeah, M2 is pulling down M1, so they're going to accelerate at the same rate. Yeah. So what we have is we have a system of equations. We have two unknown variables, A and T1. But we do know everything else. So since we are solving for A, what I'm going to do is I'm going to divide this side by M1. So T1 minus mu K M1G A. This I'm going to divide all this by M2. So M2G minus T1 over M2 is equal to A. So I'll set this equal to each other. So T1 minus mu K M1G over M1 is going to equal M2G minus T1 over M2. Okay, so to do this more, why am I doing it like this? This way is just nasty. No, I'm sorry. This way finds tension first. No. We're gonna do the other way first. We're gonna find acceleration first. And I think that way is easier. Okay, so let's isolate T1. So T1 is going to equal M1A plus mu K M1G. T1 here is going to equal T1 is going to equal M2A plus M2G. So let them just equal each other. So M1A plus mu K M1G is going to equal M2 plus M2G. But where did my A's go? Oh, A should be here. A, M2A, and M1. Okay. So M1 minus M2, sorry, something that is going to equal M2G minus mu K M1G. So A is going to equal M2G minus mu K M1G over M1 minus M2. Okay. So if we do this out, what we get is that M2 is 4 times 9.8 minus 0.2 times 9.8 divided by 1 minus 1. That's not right. What did I do wrong? Oh no, I think I did something wrong. Okay, 9.8 minus 0.2 times 4 times 9.8 divided by 1 minus 4. Oh, 4 minus 1. So you get that A should equal 0.65. And then you get the tension force should equal
Mr. Hu,
Yeah.
for M2, you put force of gravity minus tension equals M2 times acceleration. Shouldn't it be tension minus force of gravity?
For which one? For M2?
Yeah. Because then if the way you did it, the signs don't work out, but like you kind of ignore the signs.
Oh, you mean I flip this? Like, you mean I flip these two?
Kind of. Like the way you've written it, there should be a minus sign somewhere in there, but there isn't. So shouldn't the force of gravity and tension be flipped like the original, like the second line of the M2?
Oh, you mean here?
No,
Oh,
at the very start.
yeah. Okay. I see. I missed that. Okay, so T1 should equal M2G minus M2A. Here we go. Okay, so
No,
this
I
is-
think they should be added. But like at the very like first line, you put like the second line, force of gravity minus tension 1 equals M2 times A.
Yeah.
Yes. Shouldn't tension 1 and force of gravity be flipped? Tension 1 minus force of gravity.
Okay. So hold on. What did I do wrong? Oh, okay. So here is okay, so I guess usually we assume that up is positive, down is negative. Okay, so here's I guess my logic here. And we're out of time, but we're actually 1 minute over, but let me explain this real quick. Here's how I think about it. So we are assuming that this is moving, so the block M1 is going to be moving to the right? So we're going to assume that basically the direction that everything is moving in is in the positive direction. So if this is going right, M2 is going down. So if this is positive, we're setting the right direction to be positive, and we're setting this down direction to be positive. That's why I set it up this way. Because they're
Okay.
both in the same direction, so it just makes sense to set both of these directions at the same sign.
Doesn't this change the answer though now?
The conclusion is I butchered something, and let me unbutcher it real. Let me figure out what I did here. Yes, I messed something up. I apologize. Okay. So let me put it this way. The general idea is this is what you do. The reality is I messed up somewhere with my algebra, and I probably mixed up some signs, and I probably misinterpreted some stuff. Let me figure out what I did wrong, and then I'll explain what I did wrong on Friday. Okay, but thank you for catching my error. I already kept you guys 3 minutes over, so I feel really bad for my incompetence. But you guys are free to go. No homework. I'll see you on Friday, and I'll figure out what I did wrong here.
Thank you.
Thank you.
Okay.
Thank you, Mr.
All
Yu.
right.
Have a nice day.
Thanks a lot. Have a nice
too.
one.
All right, what did I do wrong? Okay, so I am assuming that this is going to right, so this is positive. I'm assuming that this is going down, this is positive, so this is fine. Actually, the thing is I flip this. Bye, Tess. So I flipped this sign. Yeah, I flipped this. So this M2A should be, this should be M2G. Minus M2A. So this should be M1 plus M2. Right? Oh, limit absorption even. Ooh. I did that. I did something wrong. Oh God, what did I do wrong? Let's explain. What did I do wrong this time?